moving on. Okay, you can read that as well as I. The methodology for calling is individual preference. But now the question is, why use them? And Todd and Randy have chosen this QSort example as a demonstration of the value and importance of function pointers. And while that is classic, in fact, this QSort example, if you go back to Kernighan and Ritchie's original book on C that defined the C language, you'll find this example. Okay? It's one that is not very obvious when we start to look at it. QSort, it's a predefined function, and one of the parameters that you pass to it is a function that actually does a comparison for you to define or to return, set which order to use when sorting. Is it bigger than this or this bigger than that? What kind of thing are we supposed to do? And so it has it has a function pointer as its last parameter, and when we make the call to QSort, compare in this case points to some routine that makes comparison. Could be a string compare, certainly an integer compare, an array of integers, another array of integers, versus an array of characters, and an array of pointers to characters, and another array of pointers to characters. Going to compare very differently. One's going to use strcmp. The other is going to use greater than or less than. Very different in the way they do things. But this QSort will use whatever is pointed at by compare to make the comparison. So we get some flexibility, get to use QSort in a lot of different contexts. All right, so this example then goes down and digs a little deeper, and frankly, years ago, the first time I read about QSort, I said, what in the world is going on? I had a harder time understanding QSort than I did understanding the function pointer business. And you may find the same thing to be true. I don't know. Here are two functions that will do, they're prototypes. They will do some kind of comparison. One compares ints and one compares strings. So we can call QSort two different ways, one with this parameter, the other with this parameter, and the list of things will be sorted appropriately. That introduces, however, the notion of having a function of one name, let's call it string, let's call it compare, just a function called compare, that can be implemented to do a lot of different things. In object-oriented programming, we call that overloading. Overloading, where we have a function name and we write it one time. Call this function, call compare. However, what it actually calls will be context sensitive or context dependent, what we give it. Does that mean that there's only one compare function? You have a compare function, the name of the function is compare, and it has two integers. That's it. Another one has compare and two floats. Both are called compare. Are they going to do the same thing? Well, they'll do almost the same thing, but one's integer, one's float. So we know that that's two different functions, two different function names, right? Should be compare int, compare float. However, we only have one function name. Somewhere behind the scenes, compare is overloaded. And we'll learn a little later in this term about how C++ mangles names and generates a new name that's unique for the function compare with two integer parameters, generates a brand new name. Call it compare squiggle squiggle. Another one compares two floats. So it will generate a new name called compare dot dot. So there's two separate names that are one of which is actually called depending upon the data type of the parameters. Same idea, very similar, and in fact this is the QSort algorithm is implementing something very similar, implementing pointers, which is what the object-oriented routines have to do.
So is the QSort an object then, or no? Structure?
No, QSort is a function, just a standard, where to go?
Function.
Just a standard garden variety function already written for you in a library that has explicitly a type here, the last parameter, is a function pointer type. And then it uses that function pointer type, it uses that function to do the comparisons for you according to what that function says.
So the compare underscore int would be a function pointer as well?
Compare underscore,
Ints or string or strings?
these two?
Yeah, those two.
What
Those
about
are
it?
Those are function pointers?
Those are function names that go into, become the, or stored in the function pointer.
Okay.
Remember, here's the definition, the prototype of QSort, and it has this as its last parameter, right? So the word compare would associate with or hold one of the names that we give it, right? And when we make the call then, here, we give it this name or that name.
Okay.
And then compare strings is passed by value. What's actually passed is the pointer, function pointer called compare, but the content of it is this or this, and that's what we wind up using. Okay? All right. So here we have compare ints, the actual functions as they might be written, and notice that it compares only one thing to another one thing, only one thing to another one thing. So these are the elaborations, the detail of how these functions actually work. But this address, compare ints, is what's passed when we make the QSort call this way. Is that clear? Don't have to rewrite QSort at all. Don't have to change QSort at all. Because it is assuming that its last parameter is a function pointer, and indeed this is. Okay? And more specifically, if we go back up a little higher in the notes, it takes const void star. So both of those functions that we would put in here have to return an integer, and they both have to be constant, which they would be. The function name is constant, just like we saw earlier, just like an array name, and pointer to, okay, of type void. So here, this goes through an example of software development, algorithm development, that does a binary search. What's a binary search, first of all? What is a binary search? Does it mean that I search a string and look and see what binary bits are turned on?
Returns true or false?
No.
It goes
Oh,
through
that's
the
right.
List by exhaustion.
Tyler?
It uses exhaustion to go through the list and test every single element down the line linearly.
Divides it by
I thought it
2?
was that-
It
cuts
cuts
the-
linear search.
First of
Divides
all,
it in
binary
half.
search assumes that the array or the
Divides
list
it into two
of data
slots.
is
That's-
ordered.
It cuts
Okay.
it in half repeatedly until it finds it.
And then it says, here's the thing I'm looking for. Are you in here? Are you above the midpoint of this list? Graphically draw that. Here's my list, and it's ordered. Here's my value, whatever it may be, and here's the middle. And so I ask, is this less than or greater than or equal to this value? I compare just two values. And since the order of this list is in order, it's sorted, what do I know if I get a result that says this is bigger than that? I don't need to look at any of this, right? Therefore, it's cut in half. The search space is reduced by a factor of 2 by that one comparison. Is that clear? Now we do it again. Knowing that this part is eliminated, now I'll find the midpoint between here and here. So now middle is here. And I'll ask the question again. Is this bigger than this, or less than this, or equal to? If this is bigger than this, once again, we know that that can be eliminated. Is that clear? Questions on that? That's the algorithm that's being described or referenced here. And binary searches are incredibly important in computer science. Why?
They're faster than a linear search?
Is it a little faster or a lot faster? A lot faster. It assumes a critical assumption, data is ordered, right? How many values are in that number? Quantity minus 1. How many values are there? If you had an array that big, how big would the array be?
1024?
What is it?
1024?
No.
Wait, what's the exponent? I can't read the exponent.
32.
It's a 32. 2 to the 32.
2 million something?
That's a 4-byte word, if you will. It's around, I don't know, somebody can get their calculator out. It's around 4 gig, isn't it? It's around 4 gig? 4 billion, right? So, given I have an array that's that size, my computer has it, right? Sure. If I had an array that size, and the data in it was organized alphabetically or numerically sorted, how many comparisons would it take to find my search value at maximum?
16.
At maximum.
32.
About 32 at maximum. 32 if statements. Is that clear? That's pretty powerful, isn't it? You have 4 billion items, and you can find the needle that's in that haystack, assuming the haystack is ordered, in 32 comparisons. That's pretty astounding. I think so anyway. And so do a lot of folks in computers. that's the algorithm we are developing here. And here's the pseudocode to do it. And here's an array of pointers. And these are ordered, we would assume, by characters here. And we can find, using a binary search, we can find the target value very quickly.